Hello everyone. Part 3 of free radical, that is stability of free radicals, and the previous two videos, that is generation and features of free radicals, that you will get in the playlist link which is in the description box. It is true that scientists are more interested in reactive radicals, not stable radicals, but if we know the factors responsible for stability of free radicals, we will also be able to understand the factors responsible for reactivity, because reactivity, stability, these two are inversely related to each other. So here we will basically use bond energy as a guide, that is the data of bond energy, so that we can understand how easily we can get radical by homolysis. So when bond energy is very low, that is weak bond, homolysis can occur easily and you can expect that the corresponding radical that will be stable. But if it is very high bond energy, then breaking of that bond is difficult process, that will not be. So here you can see four different types of free radicals are there: tertiary, secondary, primary and methyl. Now how to understand that, what will be the stability order? To understand the stability order, we will use the data of bond energy of these four radicals, that is basically bond energy of the alkane precursor from which these radicals are formed. So see, here we have this Me3CH. If you break this bond, basically you get this tertiary free radical. If you break this carbon hydrogen bond of Me2CH2, you get the secondary radical. Then MeCH3, which is basically ethane, CH3CH3. If you break this bond, you get this radical. And the last one is simple, methane. If you break one of the carbon hydrogen bond of methane, you get methyl radical. But look at these bond energy values: 397, all are in kilojoule per mole unit, then 410, 423, 439. So when you are moving from left to right, it is basically increasing. That means this one you can easily break and the corresponding radical will be stable. So the stability order is like this. And probably you are thinking that for carbocation also this is the same stability order, right? But we have to remember that okay, these points also keep in mind that this reflects the relative ease with which CH bond in alkane precursor will undergo homolytic fission. That is, this reflex means all these bond energy values. So what I am saying is that the stability order in case of tertiary, secondary, primary methyl carbocation also same, but we have to remember that the relative difference in stability is however very much less than with the corresponding carbocation. So when you are considering the carbocation stability, it is true that the order is same, but suppose you are considering tertiary and secondary, the difference between these two, that is I am talking about the stability difference when you are considering tertiary radical, secondary radical, and when you are considering tertiary carbocation and secondary carbocation, then the stability difference, these two stability difference in these two separate cases, these are not same, there is difference. So though the order is same, but there is relative difference in stability. Next we will see allyl radical and benzyl radical. Now from which we can, that is the corresponding hydrocarbon if you consider, from which we can make this, it is basically CC double bond CH2 double bond CH CH3. So here if you break this carbon hydrogen bond, basically you get a radical here which is this allyl radical. This is the bond energy 364 kilojoule per mole, and for this benzyl radical generation basically we have to break this carbon hydrogen bond of toluene. This is the corresponding energy. Now if you look at these two values 364, 372 and just compare with the in the previous slide, all these four values, basically all these four values are higher. So what I am trying to say, 364, 372, these two are lesser than the previous four values. So from this we can say that these two are more stable than alkyl radicals. Previous four examples, just compare. And if you just compare these two, which one is more stable? Obviously this will be more stable, which is clear from this data. Next we have vinyl, alkynyl and phenyl radical, and from which precursor you can make it? It is basically ethylene, then acetylene and benzene. Now look at the values. 431 when you are breaking this bond, then 554 when you are breaking this carbon hydrogen, and any of this CH bond of benzene ring, it is 466. So if you are simply comparing these three, obviously 431 that will be maximum stable, that is this one. After that phenyl, and at last we have alkynyl. But if you compare with the alkyl radicals, the 4 examples in the previous slide, now you can say that these are less stable than the alkyl radicals, which is clear from these values. Fine. Next we will see some examples of stable radicals. So here all the 4 radicals that you are seeing, all are basically stable. So radicals stabilized by functional group. Now here we have C double bond O, and in this case you can expect conjugation, and after it is not double headed arrow, there will be O dot and we will get a CC double bond. In this case, this type of resonance possible, we are getting CC double bond, then C double bond N, there is radical. Next to it is not possible, but see here all these 4 are basically stable. Now don't try to find any correlation that when there is electron donating group then only it is stable because radicals are electron deficient. No, it is not. It's their behavior, that is free radicals behavior, it is not like conventional electrophile. Conventional electrophile, you can say that they are electron deficient, so obviously they need some electron donating groups. But here that logic is not applicable. So whether the functional group is electron withdrawing or electron donating, that question is irrelevant here. Okay. So here radicals, and the reason behind it, radicals behavior are not like conventional electrophiles. So don't expect that the factors that stabilize carbocation, it will also stabilize radicals. No, it is not like that. It can be stabilized by both electron withdrawing group as well as donating group. But to understand that in detail, we have to know the molecular orbital diagram, though in a very simple way. But that I will discuss in the next slide. Also, we will see some persistent radicals examples. Fine. So stability of free radicals, that will be I will complete in the next video. Today we will end the video here. So if you find this video helpful, please like, share and subscribe. I will meet you in the next video. Thank you for your time.